was the motivation for this talk? So we started with a poll for UG first years a few weeks back, and we asked them what topics they wanted us to cover. And one of the questions was thinking about technologies with which we can travel to Andromeda. So I thought this was very interesting, and using this, we can introduce basic astronomy and astrophysics to many people. So the whole talk will be focused around answering this question, and in the way we'll be discussing many topics which like how will we travel to Andromeda, how far is Andromeda, how do we travel to Andromeda, how should we travel, why should we travel to Andromeda. So let's get started. And you can stop me at any time if you have any questions, or if you think if I have not explained anything properly, you can just stop me anytime. I don't mind. So what is Andromeda? So let me take you back to 16th December 2022. You know there's this ground where people play cricket for the TMC ground in front of the SBI ATM at ISC. So this image was taken on 16th December 2022 by a club. And in this image, you can see the most glaring feature to the left of the image are these lines. These lines are from the SBI sign post. So there was some glare in our image. But what I want to show you in this image is this small feature over here. So this blob of light which you see is Andromeda. So first I'll introduce you to Andromeda in a phenomenological fashion, and then I'll get to what Andromeda is actually. So this is another image of Andromeda taken from Ladakh by Professor in our club just 1 month back, and this image was taken with much better equipment than we had in 2022 and in much better conditions, so it shows a lot of detail which was not visible in the previous image. So a few things about this image which we noticed in the first look. So the image is smeared, so this image, it's not a point object like stars you see in the sky, and it's very large. So this image covers a huge swath of the sky. So it for comparison, the white dot drawn in this image is the size of the moon, approximately, in the sky. So Andromeda is much bigger than the moon. The moon is about half a degree in angular diameter, but Andromeda is about 2.8 degrees across. So it's about 6 times larger than the moon. How many of you have seen Andromeda with your naked eye before? Okay. So only one person I see, which is not from the club. So it's very difficult to see Andromeda. Okay, 2 people with the naked eye because it's very dim. So watching it requires special equipment or very good conditions, like that, say in the lab. So only the bright central region is visible in this image. But in this image, we have taken many exposures and we have stacked all the images to reduce the noise, and we can see the entire angular diameter instead of just the central zone. So I have drawn a small red line just beside the parts you can see in that image, but it's almost not visible. So are there other objects like Andromeda? So these are objects which are only visible below around 21-ish degrees of latitude. So if you live anywhere below 21 degrees, which includes Bangalore by the way, 21 degrees of latitude, and latitude of Bangalore is about 13 degrees. So you can see these two objects, at least one of them very clearly from here. But because there is so much light, street light and light pollution in Bangalore, you cannot see these very easily from here, but you can see them from a nice location. These are called the large and small Magellanic clouds. So I'll come to what are these, but these are also smeared like Andromeda. These are not stars. These are not starlight. So stars have a very sharp peak in brightness, but these objects are extended and cover a very large angular diameter in the sky. So, and how many of you have seen the Milky Way with your naked eye before? campus of Chennai, and that was my first time I saw the Milky Way, and it was a life-changing experience for me. So the Milky Way is also an extended object on the sky. So what are all these objects? What are all these structures? We'll slowly come to the nature of these objects, but first we'll try to describe them. So the Milky Way was known since ancient times. So on moonless dark nights, you can even see your shadow. The Milky Way is so bright. If you look at, if you stand on a moonless dark night inside a place like Ladakh, where there is no light pollution, you can see your own shadow in the Milky Way. But it's not. Unfortunately, most of us don't get that privilege. But often the Milky Way rise has been confused with the sunrise. So, like, it's so bright that you think the sun is rising up, but actually it's the Milky Way which is rising. So in Carl Sagan's series and book called The Cosmos, it's a very nice series. I highly recommend it to anyone who is mildly interested in anything which I will talk about today. To watch that, it's very nice. So he describes the Milky Way rising as not a sunrise, but a galaxy rise, a morning filled with 400 billion suns rising in the Milky Way. So it's really a breathtaking experience to look at the Milky Way rise from clear location. Unfortunately, most of us are not in the city, who have grown up in cities and stay in cities or towns, don't get that privilege nowadays. But most humans in the history of humanity have had the privilege to look at the Milky Way. So there are other similar objects with stars inside them also, like the Great Orion Nebula. So this is an image of the Orion, the lower part of the constellation of Orion. So I'll describe what is Orion in a bit, but for now you just think of this as part of the sky. And this red object is the Orion Nebula. You can barely see it, but it's also smeared. That's what I need you to know from you, just for now. So this was taken behind E-block. E-block is a possible near the galaxy, and behind that we took this image and 16 December, I think. And this is a stacked image. So we have taken around 180 images, we stacked them to reduce the noise. And you can see the stars clearly in these images. You see the stars are point light, but the nebula in the middle, first thing, it has a very different color. It's very red compared to most of the stars. And it's extended in the sky. And it's not symmetric like the stars. There is a clear asymmetry you can see. And if we get time, we'll discuss later why we have that. Okay. What are the techniques we use to? So what I'll be introducing now is something called the distance ladder. So it's a ladder. Why do I call it a ladder? You'll see in some time, because all the steps in the ladder, they depend on the distance. So if you want to climb the ladder, you need to first climb the first step, then go to the second step. So if you don't have the first step, you can never reach the fifth step. So the distance ladder is also like that. So we need to know smaller distances very accurately in order to know larger distances also. So as we keep on adding steps to the distance ladder, I'll be building the rungs. So this is the distance ladder. We'll start first with Earth. So Earth, our planet, and then we'll go to the solar system. Then we'll see how we measure distances to nearby stars. And then we'll be looking at the galaxy. Also, I'll be referring to the Milky Way as the galaxy because it's our galaxy. So I'll not be telling the Milky Way. So the galaxy. And then we have the local group of galaxies. And then at the highest ground, I'll be talking about the entire observable universe. So how do we know those distances? So I'll not be going into much detail about all the mechanisms, but I'll be just briefly telling about most of them. And then we'll have a poll at the end. If you find any topic particularly interesting, you can fill that up and we'll cover that in much more detail in the next one. So let's start with the Earth. So how do we measure distances on it? So this measuring distances on a small scale is pretty easy. You just take a ruler, or you say in the ancient days take a camel and measure how fast it goes, and then make it travel for this amount of time, and then you see how far. So it was easy to measure distances between cities. But the problem comes if you want to measure, say, the entire Earth, your oceans and whatnot. So you can't use a uniform method, and there's no hope of, like, at least there was no hope of traveling the Earth in one day, say 1,000 years ago. So how do we go about measuring distance? So the first accurate measurement of distance was given by this guy called Stardust in ancient Greece in 240 BC, and his method was very interesting. He never traveled and measured distances like I mentioned earlier. He got some scroll from a library that we were examining, and in the scroll was a detailed description of the shadows cast by two light rods at two different cities. And so there were two cities, it was Syene and Alexandria, and at the same day, at the same time, at noon, it described the shadows which they made. So one of the rods made a shadow like this, and one of them made a shadow like this. So it was known, it was not known, but it was very, like some people knew that the earth was not flat. There were many evidences pointing towards that, but the main problem was measuring the curvature. So using this and some simple calculations, as you can see, he could trigonometrically measure the angle which was subtended by the arc containing these two cities from the center of the earth. So using this, he knew the distance between these two cities, Alexandria and Syene, and it was, I think, done to a very good accuracy. There is some dispute about what the stadia unit was back then, so we don't have a clear record of what it was. But if our guesses are correct, then he measured the Earth very accurately. So this was the first measurement of our planet, and now we have very good techniques to measure the planet. We have radar, we have GPS, and whatnot. We can measure the planet in multiple ways nowadays. But this was the first method of measuring the planet. Now I think we deserve this, and we know what distance scales on Earth. Now we'll talk about distance scales in our solar system. So what is our solar system? We'll start with that. So what are planets? You see many stars. Okay, how many of you have seen a star in your life? Like star, a real star with your eyes? Some people really don't see it till a surprising age because they're so in such a bad geographic location. So, a star is a point-like object on the sky, and when you see a star, it moves in a certain way, and those movements are very periodic. And if you look at the sky over a period of time, you can predict those rhythms. And most stars move in circular orbits throughout the sky. So if you look at it throughout the day, the star will be rising in the east, to a great circle, and it will be setting in the west. So what makes planets different? See, people knew about planets before the invention of the telescope. So in fact, in modern literature, the names of the weeks are named after planets. One day when you say Thursday, all these have a one-to-one correspondence with the visible naked eye planets. So people knew about planets way before we had the image of, say, Jupiter with its giant gas rings and whatnot. So planets are objects which do not follow this circular path over a period of time. So if a star moves like this, it will move like this the next year also, the next day also, and every day with respect to this time. And all stars will follow their own orbit. But the planets will move with respect to this. So they will follow some very complicated orbits, which look very complicated in the beginning. And the ancients only, they only had observations at night. So one day they look and see, say, this star, which is reddish in color, and now we call that mass, it will be over here. And the next day it will be over here. And the next day it will be over here. So with respect to the background stars, the planet will be moving. And this movement is very erratic. So just to show you few months of 2003. So you can see the path this object makes, and these are background stars, and these are just the names of the stars. That line called the ecliptic is basically the orbit of the Earth's revolution axis. So how do we explain this motion? So that was one of the biggest problems of antiquity, and we tried to get it. And the name planet means wanderers in Greek. So like they called them wanderers who wandered about the stars. So what were these objects? There were 5 of them, including which were visible. So okay. So now these planets, even though they move very erratically, everything has to move like that. So they tried to explain this erratic, seemingly non-circular motion by considering something called the epicycle theory. So what they considered was, so there was this orbit, and then there is one more circle. Arbitrary number of circles, you can eventually show any motion on the star. But they came up with fantastically complicated models. They even had mechanical models showing how these things move, but still they were not satisfactory because it was just a phenomenological description of what was happening. There's no arbitrary reasons for the circle to be, like say, a radius r. So they just fit the data with whatever circles they found work, and that was the theory for 2000 years. The best theory we had for the movement of the planets. And there were sciences back then called astrology, which would predict everything from how you live to how you die using these circles. So, but then came a change. In the 1530s, there's this Polish priest called Nicholas Copernicus, and he came up with a model which suggested that the planets were actually, like, the Earth was at the center in the beginning. So all the circles were centered around Earth. The Earth was the center of everything. That was the idea before this. But then Copernicus came up with this idea that no, all the planets don't move like this. The sun is at the center, the large bright ball which rises up in the day, and then everything else moved in circular orbits around that. And it made sense if you thought about it logically. So there's one thing called the retrograde motion. So these epicycles created a very convoluted way to explain this backward movement. But in this model, you can see that if there are 2 circles like this, 2 orbits like this, and say Earth is also moving like this, and say a planet called say Mars is moving like this, the relative velocity can for some time be backward. So if the Earth is moving faster than this, so you think that this angle is changing back in a backward fashion, not in the direction in which it usually moves. So the retrograde motions make sense, but back then it was very unorthodox for something like this to be accepted, and Copernicus was very afraid of publishing this because the church was absolutely against the heliocentric. So he refused to publish it until he died. So his student called, I think his name started with Errata or something like that, I can't pronounce it, but he convinced Copernicus to publish it when he was dying. So in 1542, he finally convinced, and there's a saying that he died just last day his book was printed. He looked at the book and that's the So then over time people realized, and the epicyclic theory there was more heated debates over the word, which was the model which was true, and then came these 2 people, Tycho Brahe and Kepler. So in the 1600s, Tycho Brahe was a very wealthy man. He had connections with royalty back in the city, and he was very intelligent. He lost his nose in a school fight. And he was one of the greatest astronomers, visual astronomers before the telescope. So all the measurements which are made by these people were made with naked eye equipment. They didn't have optics or lenses or mirrors, anything like that. They just used the position of the sky and measured angles. And Tycho Brahe had excellent data for many years of all the motion of all the visible planets. And he hired Kepler to analyze that data. Kepler was a mathematician, everything. He was in polymath in the same. And what Kepler observed, changed our understanding of the planets forever. So if you consider circular orbits and the heliocentric plane, and then you plot all the points in which, say, a planet, Jupiter, or say Mars or Saturn will move, you can get a locus of all the points at which you will expect the planet to move in the future. So you need four points on the spherical surface of the sky to determine exactly where a given planet will be. So, like the orbit of a given planet. And the fifth point will verify if what you predicted the orbit to be is the correct orbit. So, if the orbits are exactly circular, you should see you see 4 points, and then you can predict the fifth point. If you interpolate the circular orbit in the sky, obviously. This is just a 2D representation of the data. So, Brahe was an excellent observer. So he had so the human eye can see up to 1 arc minute. So that's 1/60th of a degree. And so the resolution of the human eye is 1 arc minute, and the resolution of which Brahe got in most of the stations was about 2 arc minutes. So if it was off by more than 2 arc minutes, you may be sure like Brahe won't get that. So all the planets seem to obey that law, but one of them, which we now call Mars, seemed not to obey that, and it differed by a whole 8 arc minutes. So this comma means arc minutes. So 8 by 60 degrees. That's a huge amount. So it's 4 times more than the upper bound which Brahe should have. So this seemed not to work. So Kepler just got rid of this idea of circular idea. So 3,000 years of this idea of holding on perfect circles and perfect spheres just broke down in that moment. So Kepler then tried to get the curve which these planets follow, and just with empirical data. And back then we didn't have calculators, so everything was done with ruler and pen. So he got the orbits to be following elliptical orbits with the focus, the sun at the focus. So this is a very exaggerated view of the orbit, but it was not circular, and this changed everything. So there was this famous 3 laws of Kepler which he got empirically using these observations, and Kepler was incidentally nearsighted, so he never saw the stars properly. If you're nearsighted, you can't see the stars without goggles. So he never saw the stars. He just had the data from Brahe, and he was also told that he was the first person to hear the harmony of the universe. So after Kepler, one more point which I mentioned, which is very interesting. He did the same analysis for Saturn, Jupiter, Venus, Earth, and all of them were within the 2 arc circles. This is because the eccentricity of those orbits are very small compared to the eccentricity of Mars. Mercury is a different game. Mercury is very eccentric, but it's inside the Earth's orbit. So Mercury and Venus are inside. So you can't get the same kind of measurements which you can get for the outer planets. And Mars is just bigger. So if this is Earth, this is Mars. So because the eccentricity of Mars is just higher than that of the other planets, he got that 8 times. So if we say in an alternate universe we lived in a solar system in which we had no Mars, I think Kepler wouldn't have seen that data, and it would have been a lot more to discover this fact that the elliptical orbits exist. So now we empirically knew that the planets follow elliptical orbits, and the scale of the solar system became. We could use trigonometric measurements, and there's this famous 3rd law of Kepler, which related the most semi-major axis of this ellipse. So this is the major axis of the ellipse, half of this, with the time period it took to move around it. So that was just measured with empirical data, and it fit beautifully with all the curves. So with this law, just by measuring the time period, we could get the length scale of this orbit, and using that we can use trigonometry and find out the distance scale of all the planets, so the ratios, and if we know that one of those distances, we can figure out all of them. So the solar system had a distance scale, and then after he empirically discovered this law, 100 years or so later, not 100, less than 100, around that. So there were two people called Galileo and Newton. Now, Galileo was responsible for the discovery of, among many things, the preliminary laws of motion and the telescope. So he was the first person to build a telescope which was used for astronomical purposes. There were lenses and there are other stories, but he was the first person to point that, at least in written registry, to point that as a star. So, and Newton, all of us know about Newton. So, there's this fun story. Newton discovered the laws of motion very early, and he never published it. And one day, three people, I think Christopher Wren, Newton, and Halley, the famous Halley, Edmund Halley, was sitting together, and they were talking about this weird law of Kepler, why are the planets moving in elliptical orbits. And Newton was like, 20 years ago, I just proved that it should always follow an elliptical orbit if the law is something like this, the law of the force, as he called it. So, and then, but he didn't ever publish it, and he lost all the manuscripts. So then Halley convinced him to publish his work. He even paid for the publishing of the Principia for the first time. The Principia Mathematica is a book which introduces modern calculus, and it is the basis of the mathematics of all the orbital physics which we know about today, and all the calculus we know. Half of the calculus is mathematics also. So it took him 3 years to replicate the work which he did 20 years ago, and then finally he published it and wrote it in Mouns. So now we had actual laws which were describing the motion of the stars, and now we have a very firm understanding of why the planets are moving the way they are. So we started with epicycles, and now we have a rule, a God-given rule, so to speak, to measure this. And so this is just our discussion for the solar system. And the solar system distances, modern day measurements are done with radar. So we use radio waves, we bounce them off other planets and see how much time it takes for the radio waves to come back. Using that, we have extremely precise measurements of distances in our solar system. And this is very crucial because all the other distances depend on this distance. So we have this pattern now, and it's very accurate. So the distance to the sun was measured to an accuracy of a few kilometers, and we know it's around somewhere in the range of 10 to 11 kilometers. So that inaccuracy is around 1 in 10 to 11 or 10. So we know it very precisely, and this will enable us to go to the larger scales that we talk about. So how do we measure distances? Okay. Yeah.
In the slide there is mention about transit method. What is that? And can you also explain?
So that was the trigonometric methods which I was talking about. So I'll not be going into much detail for every method. We have separate talks for those if you know many people are interested. So the Venus and Mars have orbits inside that of Earth.
Mars.
Sorry, Venus and Mercury.
In the slide it writes.
I think it's wrong.
Okay.
So it's Venus and Mercury have orbits inside that of Earth, and the orbital planes of these planets are very parallel, but they are not exact. So the orbit of Mars is maybe something like this, and the orbit of Venus may be something like this. So the only time when you can see them in a straight line together from the perspective of Earth is in the place where they intersect along your lines, where the orbits intersect. And this is pretty rare. So for Venus, I think it takes around 125 years or something like that for one transit to occur. So the last one was, I think, somewhere in 2014. I don't remember. I don't know. But, so we don't have a hope of doing that, I'm sure. So if you see Venus passing through the disk of the sun, so Venus will pass something like this, and you can measure the time it took to pass, and then you can do some maths and you can figure out what the exact scale ratios of the distance to the sun and Venus and the size of the sun. Everything. You can figure out everything using these kinds of methods. Yeah? Yeah, we need to know some initial distances, and those were gotten by other methods. So there are many methods, like you use the shadow of the moon, there are many methods to know the lunar distance. You know one of the distances using the we know the time period, we know the semi-major axis of this period. And then measure this time and then we can some other variable. I don't have the exact details of my head, but using Kepler's law, you can figure out the entire distance scale of all objects. Yeah, so that's the question.
I think told right now. Right now we are measuring the distance to other planets using radio waves.
Yeah.
But let's say a planet is too far away.
Yeah.
And if we emit the radio wave, it has a finite speed.
Yeah.
It won't be like in a place of incident move from its original.
Yeah. There are many other effects also. So there are special relativistic effects which we have to take care of. The time in the different frames will be different. So, but people have done all those calculations, and doing all that, like, to a first order calculation, those effects don't matter because the speeds of the planets are very small compared to the speed of light. So they don't change. Like the planet won't be in a significantly different position, but still there are some effects. For example, the relativistic effect was first observed. The Jupiter has these moons. There are many moons of Jupiter, and the transit times they seem not to be fixed. So they don't follow the Keplerian law, so to speak. So they have this. Sometimes it's 11 minutes earlier, sometimes 11 minutes later, and we can explain that using the finite speed of light. So back in those days when these things were first figured out, we had no idea about the finite speed of light. We thought light was instantaneous. So but these were one of the first hits of the finiteness of the speed of light. Then there are experiments like Mouns and other things which were very good.
Small question and a small question. You were talking about the shadow of the moon observing that.
Yeah.
So the question is, apart from the eclipse, when this can be seen?
The shadow of the moon. Yeah.
When do you see it? And how do you see it?
So when I talk about the shadow of the moon, there are many things. If the moon is, say, the Earth and moon are in a straight line, then we can see the moon in front of the sun. And if it's behind us, we can see the shadow of the Earth. We can measure the time it takes for the shadow to move across. We can if we just consider the orbital motion of the moon, and we look at the percentage illumination of the moon at different phases, we can figure out a lot of things about the relative angles of the orbital motion. So these things are very trivial now when we think about it, but when these things were first figured out, like I think the first measurement of the Earth-Moon distance was the decibel. So someone assumed how much the moon was illuminated, exactly what the quarter phase, and then they found out what was the distance. So these things were very non-trivial back then, but now we can take an image of the moon and we can exactly count how many pixels we have, and then we know the solar distance scales very precisely. We don't need to invoke shadows, but shadows were very important back then. So this is all about the solar system. So now I think we have covered the solar system, and we know, we are pretty confident about distances in the solar system. So how do we measure distances beyond the solar system? That's the question which we will be. So this was the first method which we used to find out the distance to the stars. So how do we measure the distances to stars? So people figured out pretty soon that if the stars were not very far away, we could in theory measure this distance using this method for the parallax. So what it suggests is that we know the Earth is moving about the sun. So if we take that as a fact, and we say the Earth moves like this, and there's some stars reducing, and there's some very far away star feeding. So if you look at the stars, say at June, and then say at December, very far apart, almost opposite parts of the orbit, you'll see the star in different angles. So there will be a small deviation at the point theta in the spiral orbit. So this deviation which we find in the orbit was supposed to be measured but nobody was successful in measuring it because this angle is very small. So even for the nearest stars, which we now know, it's of the order of a few milliarc seconds, of the order of few arc seconds for the nearest stars, but in general it's very small. So measuring this is very hard. So in order to measure this, many people tried, but many people failed. So this is how it should look. So if the star is far away from the star, you should see some change in that. And this change was like with Galileo and the many modern telescopes. People tried to measure, but they were unsuccessful until 1832, in which they observed something like this. So this is what we expected. So this is Proxima Centuari, nearest star, one of the nearest stars to planet other than the sun. And this is not from using this method exactly. So there was this probe called the New Horizons probe, which is a space probe, which is now flying off away out into the outer solar system. So these are two images taken looking at the same field from New Horizons and Earth. So the same principle applies. You're looking at from two different positions, and you see the relative change of this star, which is much closer to us compared to the background field of other stars. And with this, we can now measure the stars. We know how far the stars are. And the stars are very far away. So we measure stellar distances in the order of light years. So this Proxima Centuari, the star which saw just now, is about 3.2 or something, 3.2 light years. So light will take 3.2 years to come from that star to here. So light from say 2021, which left the Earth from 2021, will be reaching that star. So one of like Tycho Brahe, who was the observing guy of Kepler, he was very he never supported the heliocentrism even after Kepler's work. So he died before Kepler. But one of the primary reasons for him not supporting the heliocentric model was that stellar parallaxes was not observed. He expected this, but we never saw stellar parallaxes. And after many such work, in 1832, 1838, we saw this parallax. We measured it. So, but parallax has some limitations. So, the main problem with parallax is that if you measure parallax, the farther away you try to measure the parallax of an object, the angle goes very rapidly. So the smallest angle you have to measure in order to measure accurate parallaxes goes up. So I'll just this is just a bit of just to show you how this works. So the distance follows the distance of the star is 1 by the parallax angle. So say the angle is 0.1, so the distance will go as roughly so this 1 by d. So the change in distance of the parallax should follow a relation which is something of the order of so if you don't get this, it's okay, but just take my word for it. It's around the order of 1 by dt by d square. So the smaller your parallax is, farther away the star is, the distance estimate you get will have larger errors associated. So the most accurate method we have now to measure parallaxes is using some space probes which do interferometric parallax, another method, but the main principle is same, and they can measure distances up to a 10% accuracy, up to 25 kiloparsecs. So 25 kiloparsecs doesn't even cover the entire Milky Way. So we can only measure parallaxes for nearby stars accurately. We can measure parallaxes, but they grow very rapidly. So, and they grow as 1 by d square. So the angle, if the angle is very small, we have a very large so 25 kiloparsec, this unit parsec, just to about 3.26. We know now the distances to nearby stars. So how do we proceed from here? How do we know distances which are much larger than the distances to the nearest stars? So there are these stars called C5 variables. The first star of this type was observed in the constellation of Cepheus, and they have a very interesting relationship. So we knew that this this periodic pulsating pattern, and they seem to be very correlated with the distance which we measure using parameters. And so if we know the brightness of a star, say on the sky, we can't figure out its distance because it could be a very bright object very far away, it could be a very dim object right at our place. So we need to figure out a way to know the distance independent of the intrinsic magnitude of the star. So the intrinsic magnitude of the star was directly correlated with the C5 frequency, which was the frequency in which these pulsations were. So these stars form the next step of our distance. So using parallax, we figured out the distances to many stars, all the stars which were in our neighborhood. But we could go further using C5 search. So if we discovered a C5 star which was out of the range of parallax measurements, we could know its absolute magnitude, and then so if we know how bright it is at say 1 light year away, and we see that it's not that bright, it's half that bright, so we know that it's root 2 1 light year, so root 2 light years away in the air. So using C5 variables, we can go further, but discovering C5 variables was hard because C5 variables are relatively rare. So you can see about 4,000 stars with the naked eye in a very clear night through the entire sky, and C5 variables are much rarer. So only the closest, brightest C5 variables will be. So, but with time, as optical instruments increase and we observe many more stars, we figure out to observe many more C5 variables. And the eureka moment in this part comes when this person called Edwin Hubble, he discovered a C5 in Andromeda. So in Andromeda there was this sea of stars, and people had just begun to resolve stars in Andromeda. And he had this plate. So back then we didn't have detectors, so we used chemical methods to detect the lights. So there's these photographic plates, and you had to develop them in a dark room, keep them in the dark. There was a huge process. It was not as easy as clicking on a button. So he found a variable star in that plate. So this was the actual plate, Hubble plate. And once he discovered a C5 variable, he visually figured out its distance. We know that distance now. And there was this very big debate about was the Andromeda part of our universe, or was it a different? Because you could clearly see some structure over there. It was nebulous, but it seemed very different from all the other stuff like Quran things. So some people, like the philosopher Immanuel Kant, he believed that they were other island universes. So these were all stars in the galaxy, and they were completely detached from our own. So the Milky Way had no role to play with that. They were very far. The other people who thought that they were like part of our galaxy and they were inside some structures inside our galaxy. But with the Hubble plate, it was very glaringly certain that this cannot be part of it. Because we have a rough idea of the size of our galaxy using the parallax method and C5 variables. And this was way further than that. So our galaxy, the distance from, if I draw the galaxy, the Milky Way, if I consider Milky Way to be a circle, and the distance from the center to our sun is about 7 kpc, which is around 7 kpc, which is, so K means 1,000, so 7,000 thousands. So, and Andromeda was 2.5 billion light years. So this is very far away. So billion light years means light will take 2.5 billion years to travel this distance. So Andromeda was not part of the Milky Way. So I don't remember the distance calculations exactly, so I will include it in the minutes. So it's very far away, 2.5 billion. It's well beyond the Andromeda is not inside the Milky Way, but we know that. So there are other galaxies which are not part of the Milky Way. So with using these methods and some other methods which are just touching in the next slide, we now know the location of all the neighboring galaxies. So the local group, as we call it. So these are the galaxies which are closest to us. So the center of this image, the circle, is the Milky Way, and Andromeda is that big thing you can see in the upper left. So you can see that clearly the distance scales are very different for the Milky Way and the distance to Andromeda. So there are all these small galaxies, dwarf galaxies, which are orbiting the Milky Way, and all of them are have very, very erratic orbits. So, how do we measure larger distance? How do we go larger than this? So, there are some methods. So, light is most of the information about these objects comes to us from light. So, a very big proportion of what we know about, say, everything we know about galaxies is from that. So, we use spectral lines and something called redshift, which was also there's this idea that if a light wave is emitted from a source, so it has a frequency, and because it was an experimental fact, which was also discovered by Hubble, that all the galaxies seem to be moving away. How do you measure that? Because what should happen if everything is moving away? This light should be shifted because the expansion of the universe. So the space in between the source and the object is itself expanding. This will cause the wavelength of the light to increase. So this increase in the wavelength can be measured. So if we know, say, an hydrogen atom emits at, say, this wavelength, and when we measure those emissions at a different wavelength, we can figure out what's the velocity with which goes up. And this velocity had a linear relationship with the distance. This linear constant was called the Hubble constant. So, and there are other events called type 1A supernovae, which I'll talk to a little bit. So, supernovae are, just to give a phenomenological description of supernovae, you look at the sky, one day there's nothing, but the other day you see bright sky, pop out of nowhere. So, that's basically a supernova. So, what is that physically? We'll come to that later. But these events were noted throughout time. People by measure world, the ancient Chinese, which grand and largest, which is also visible. So, these supernovae events can also be used to calculate. I'm not going to detail about these methods, but the largest scales of the universe can be known using these methods. So, spectral lines, redshift, and supernova. So these are the next terms of our discussion. So we know the Earth, the solar system, then we figure out nearby stars, then we know the nearby galaxies, and now we know the entire observable universe. So why do I call it the observable universe? So as I said, light will get stretched. So after some point, if you move far enough away, the expansion rate is so high, the expansion rate increases with distance. So the expansion increases with distance. So the light will never end up reaching. So there's a physical limit to how much light you can observe. So that's the boundary of what we can observe with light at least. So that's the furthest we have ever seen. And the light coming from that's very far away. So it's comparable to the age of the universe. So light coming at the beginning of the universe would have taken that much time to reach us. It's comparable to that. So now that we have a good idea of the distance scales, I'll just show you some of the largest scale structures which we know about. So distance scales can be covered in separate talk. Like each of these slides can have a separate talk if we go into details. So the galaxy superclusters and clusters of galaxies. Galaxies are not uniformly distributed throughout. So there are places where there is a very large density of galaxies, like the local group, and there are other superclusters. So there are places where galaxies are very abundant. There are places where there are no galaxies. It's very empty. So if we were, there are these places called voids. So in those regions there are almost no galaxies. And like if we were living in a void, the earliest detection of another galaxy would have been in somewhere in 1962. So it would have been very recent. So our technology would have to be that good to see a galaxy if we were living in a supervoid. And there's something called the cosmic microwave background. Go into details. And we know a lot of stuff like most of the matter, gravitational matter in the universe cannot be observed with light. So we know from modeling the gravitational interactions of galaxies and other large-scale objects that something doesn't add up. If we measure the light from all the stars and all the objects which are visible by using light, and if we add all of them, we get something which is only about 30% of the mass we expect, and 70% of the mass is moving. So we don't know if it's a mass or it's a change in the equations of motion at those large scales. So So we call those observations dark matter. So we think there's something which is not visible. And there are many other properties which we can have. A series of talks on dark matter, and these are the frontier questions we now have with the Astrophysics. So this is the Hubble Ultra Deep Field. So this is an image which was taken by the Hubble Space Telescope, and every point you see in this image is a separate galaxy. It's not a star, it's a galaxy. So each one of them is an island universe. So each one of them has millions, billions of stars. So Milky Way has 400 billion stars. So 400 billion stars are found. There are many worlds which are visible. So this was taken by just pointing at the part of the sky which seemed to have nothing. But when we observe it for days and days and days, we start to gather enough light and we can see these objects very clear. So, and the large scale structure of the universe there, that's what I was talking about, the concentrations of matter, the concentration of galaxies, the places that there are no galaxies. So it forms kind of a web-like structure. So we know this. So this is the uppermost round of this scale. No, this is an image from a simulation. So, but the observations match with this. So you can't get this bird's eye view of the entire observation. Okay? You can model this stuff. You should see the galaxy distributions like this. So now we'll move on. So everything we know about this problem. Light is very precious to us. So light not only gives us information of the present day, it gives us information from the past. So it makes us virtual time travelers. So we can see events. So for example, light coming from Andromeda, the way we see Andromeda now, it's 2.5 billion years ago. So we weren't even Homo sapiens then. So we can really peer into the past using light. So we can see the evolution of the universe throughout its history. And there are many methods which I will not go into, but light can give extremely precise measurements. So there is this thing called the deionization of the universe. So initially everything was ionized and cooled down, and again ionized because of starlight. And we can measure that using a famous radio line called 21 centimeter hyperfine transition of hydrogen. And hydrogen is like a molecular hydrogen. So it emits a light, emits a particular 21 centimeter, that's the wavelength of the light. And this light travels, and because it's shifting red, as it travels, the elements which are in between us and the source get absorbed in a particular way, and because it's shifting, it gets captured in all the frequencies. So I'm not going into much detail about this. There's something called the 900 for forest. So using that, we can figure out when the universe started to give ray analysis, call it cosmic law. There are many things. So, but we can get very detailed information from light. Light is the only source we have to prove the universe at these states. There are some other sources, but the information you get from them is very useful. So now we'll talk about how we prove it. So what are the tools we use to see light? So telescopes, noise, they are very crucial for our understanding of everything which we have touched. So I just give a brief account of what we see. So the sun peaks at around 500 nanometers, almost across the visible range of the electromagnetic spectrum, and the atmosphere distorts all the light that comes from the atmosphere is not nice. Overall, let me make this clear. The atmosphere is a good thing. So you can breathe, you can live in it, but it's not nice for observing things like that. So there's just something called seeing. So there's turbulence, thermal turbulence at the upper layers of the atmosphere, and because of that, light which comes to this pristine light which is coming from 2.5 billion light years. It's traveling for 2.5 billion light years unperturbed. It just at the last few meters near your telescope, there are these thermal waves which change the reflective index and destroy all that information. So there are other methods like adaptive optics, and which we are trying the best ways to send telescopes in outer space. So that's why they're expensive. A lot of resources. So, but still, we can do a lot by observing from the ground. Even after bad seeing, because we've seen the turbulence, you can observe many things. Images which you guys have got from the calendar, all of them were taken through the Earth's atmosphere. So the Earth's atmosphere filters everything we see, at least which is known. So this is the absorption spectrum of different electromagnetic waves, the entire spectrum. absorbs most of the light which comes to us, so most of the frequencies. But there is a small gap in the visible range, and it's the peak of our sun. So the radiation of our sun follows a curve, and most of the radiation it emits is at the visible range. Probably that's why we are able to see light in those distance, those wavelengths. So it's the most abundant light which comes in the sun. And there's this huge peak in radio. So around from say around 1 centimeter to 10 meters. You have this, the atmosphere is almost clear, that there's no perturbation at that place. So radio astronomy also gives us, so there's this different field in which we use radio waves to measure light, and we get very good information about, so there's 21 centimeter length it falls in that range. So you can observe that practically unhindered. That's why there are no radio telescopes in space, because it doesn't matter if you have that atmosphere, it doesn't affect it, because it's completely transparent. So that's how we measure. So telescopes are very nice objects. So there are two types of telescopes. I'll just be giving a brief overview of the telescopes we have in our club. So we have two types of telescopes for optical telescope. So the refracting telescope, so it basically refracts the light and focuses it into a sensor is of any director, and there's some other reflecting telescope. This here is a reflecting telescope. This is a notice that is always position. So this uses mirrors, and this has certain advantages. So most big telescopes nowadays are reflecting because they weigh less, they don't need to worry about chromatic aberrations. There are many advantages of you only need at least one surface will do, the reflecting surface. So for refracting telescopes, you need to polish many surfaces, and these surfaces have to be polished to a very high accuracy. So comparable to the wavelength of light which we are seeing. For optical wavelengths, that's around the order of a micron, so half a micron as the peak of the sun. So you need to get that surface polished way below that, so that the surface roughness doesn't deteriorate. So now we see the problem with going to so far away. How we can the theme of us how we started with this. So how we can so and give a small example. There's some things which travel intergalactic distances. So those have the name called cosmic rays. They are not rays, they are not light. They are very high energy particles which travel very fast. And they hit our atmosphere and they produce a shower of particles. So they are like the particle detectors, nature's own particle colliders. So they have energies of the order of the most. They have energies of the order of something like 10 to the 20 eV. So that's a lot. That's really larger, orders of magnitude larger than the best CERN detectors we have now. So these are the only samples of matter which we have at those distance scales, and we can measure them, use their properties, but stuff can move that far. So there is these particles called muons which are generated in the upper atmosphere when one of these high energy particles collides with the atmosphere. And what we know about the muon is that it's very short-lived. So it only takes the half-life of a muon is around, so half-life means the time in which half of the muons in a given sample will decay is around 1.5 microseconds. So it's very small. And if you calculate, it just doesn't make sense. So the muon, if it is produced here in the upper atmosphere, even if it's traveling at the speed of light, say it's very close to the speed of light, it should be reaching the surface. But if you have detectors over here, so there are these things called cloud chambers which are called ionization, they get a shower of muons. So how do we detect them? So we detect them because there's this thing called special relativity. So when you move very fast, time slows down. So the half-life increases. So it's not 1.5 microseconds. 1.5 microseconds in the rest frame. So it's not 1.5 microseconds in the frame of the muon, which is moving almost at the speed of light. So we can detect them over here, even maybe using that. Maybe if you can go very fast, say at the speed of light, time will slow down first. So if I start moving towards Andromeda now, and I am say 20 years old, and I move 99.99, and time will almost stop for me, then maybe when I reach 21 years old, and all of you who are staying here would be very old. So we can make time locally slow, but going to 99.9999% of the speed of light is not feasible. So it's not at all because it's not linear. So you can't just add, and you need an infinite amount of energy to reach very close to the speed of light. So how do you get rid of that? So I'll be assuming that there's no major breakthrough, and we don't get speeds like this, and we travel at only say 50% of the speed of light. We develop something to use all those all the uranium and we create a rocket which can travel interstellar at say half the speed of light. And it's in theory it's possible. So 30% speed of light is possible from whatever. But the environmental disaster if we start using nuclear. But say if we use nuclear fuel, we can go at 30%. A multi-generational interstellar fuel then starts to become feasible. So we can start now. So the closest star, as I said, was Proxima Centuari. It was 3.26 years ago. So if you got the speed of light, it is 3 years. So you got half the speed of light, which will take around 6 years. So in 6 years, we will reach the nearest stars. So it's possible that say even if you don't reach half the speed of light, even if you reach 10% of the speed of light, which is still a lot. We can, in theory, reach to the nearest stars in our universe. And if we can hop through stellar systems like this, we can eventually realize the dream of sailing through the Milky Way. So we will be doing radar measurements, measuring new planets, teaching our kids everything we have learned, and telling them that when you grow up, you go to the star, which is the industry. It will take you 40 years of your life to navigate, use everything, all the knowledge from Kepler to the Stardust, a lot of stuff we will find planets which are resourceful, and it will be humanity's greatest thing. So if we can do that someday, it will be an amazing sight. So we'll be observing large gravitational fields, very large objects, much larger than the sun, observing stars which are observing some things called compact objects, only the light from and there are these things called globular clusters. So there is this. So these are collections of stars which are very close to each other. So in the entire density of all these stars will be packed in a region of say 3 light years. So that's about the distance for our closest star. So there will be hundreds of thousands and millions of stars just packed in. So imagine the sky from such a planet from thousands of stars in the sky. The sky will be bright. Just imagine the future we can manage to but as it turns out, we don't have an option. We have to travel to the stars. And if we don't travel to the stars, we will die. Because there are many things. The supernova I was talking about. So it turns out these are basically the death of stars in the system. So when a star grows old, it has no more fuel to go, it has no more waste to produce the energy, it blows up. So stars eventually die. Unfortunately, every word I'm speaking now, every thought in the brain comes from the energy of doing that work comes from our sun. Ultimately, it comes from the sun. And the sun is eventually going to die. It's not going to go supernova. Eventually, the sun is too small to go supernova. We know a lot about stellar mechanics. So we have very good theories for knowing about stellar mechanics. Lifetimes of stars, we have looked at all the stars. We know that if any star is greater than say 4 masses of the sun burst, and if it's large, even for a sun, something like this will be. So this is the story, as I said. So a sun is very small. So as time goes on, the hydrogen inside its core will start depleting. We start doing other things, oxygen. And once that starts happening, because of the way the stars are structured, it will puff up. So basically, it will become larger and larger and larger, and eventually it will be engulf the Earth. Orbits of Mercury, Venus, Earth. That will happen in about 5 billion years. So that's a long time from now. still, even if you consider 1 billion years, the sun is still going to increase in brightness. So the intensity which we get now is not the intensity which we got say 4 billion years ago. So life will become more and more difficult in this solar system. So the sun will heat up the planets to a degree which will probably not be nice for life. So man eventually will die. So just pop up and then we have to go. So we don't have an option. We have to travel to the stars. It's not a question of if, we have to do this. So the stars are the givers and takers of life. So stars gave us all the energy we ever needed for life to flourish, and eventually they take that away. They die, and everything you see in this life is made inside the stars. So all the elements which are which you and I are bodies, except the hydrogen. The hydrogen is and all of these elements are made of stars. They give us matter. They give us matter and they eventually take the heat back. So there's this. We know all this because we have a lot of data about the population of stars in the galaxy. We know some of the stars are very rich in metals and they are very old. So they were formed from the primordial matter which was there after the Big Bang. And because of that, they don't have the heavier elements which in astronomy we call all elements above hydrogen and helium metals, because they are different from a different process inside the star. So we know a very detailed picture about how all of this works. So we know how, say, beryllium was formed, chromium was formed, iron was formed. We know very good models which match exactly with observations, and we know how all the elements in the periodic table in the stars. So all of these are explosion events. So these things which you see like neutron stars, these are also stars, but they are different stages. These are something called compact clusters. So after a star dies, these are the remnants, so to speak, which are left inside. So we have a very good idea about them. So we know which stars to pick. So the large stars will die out very soon. So the brightest star, which you can see in the night sky, is called Sirius, and it is very large compared to our sun. So it is a few or 8 times the mass of the sun, something like that. So that's like that, but it will die very soon. So it will die only in a few million years, whereas the sun has been burning for 4 billion years. So the larger the star you have, the shorter its lifetime is. So these stars are very good for us because all the elements we are made of are made in those stars. So those stars have the carbon, have the oxygen. They seed the other surrounding material with all the elements which make life possible. So and we need stars which are long-lived like the sun, and the stars which have ages of very large ages. The current age estimate of the universe is 13.8 billion years or something like that. And there are stars for brown dwarfs which have age time scales of about 8 trillion years. So they can live up to 8 trillion years. They will not end up burning down. The heavier you are, the faster you burn out. So we have to choose the stars we visit. We have time scales. So we can have something like galactic civilization with species spread around stars. Some of them will have to live because the star is that long. Some of them may live up. But there's this, once we have reached the Milky Way, this stuff kind of, because you saw that image of the local group, right? You saw the distance scales. There's large distance which are almost no stars, and it was in between Andromeda. That's called something called intergalactic region. It's very like the density over there, everything is less. So we don't have a hope of traveling through that. Like if we assume that 90% of the scale of stuff like that. So are we stuck? So what should we do? Will we ever cross that issue? Luckily, the answer turns out yes. So I mentioned these red shifts. So all the galaxies seem to be moving away from us. So all the far away galaxies. Locally, some of them just have random velocities. The random velocity oscillates over the expansion. So the expansion rate increases is Andromeda, and it's moving towards us at 300 kilometers per second. So eventually we are, in fact, as I speak, we are traveling towards Andromeda, and the galactic position of Andromeda is incredible. So if we just survive in this island universe, eventually the island universe of Andromeda will be merging with the island universe in a few days, and we will be in Andromeda. So the question is, can we survive till Polu? Maybe if we try hard. So everything we do depends on everything we do now. So frankly speaking, none of us in this room have our hope of Andromeda. But what we do now will determine if our descendants will. Maybe we'll just destroy ourselves and we will Proxima and when Andromeda reaches us, we just attend up. Or maybe we just don't decide to leave our sun. So we just end up and being engulfed by our own sun, and we will be part of something for a while. But if we decide to study everything and teach our descendants all the knowledge we have, eventually maybe one day we will be visiting Andromeda. It depends on us right now. What are the future of our descendants will be. It's not just physics or astronomy. We'll be acquiring so many things. We will require huge advances in, say, biology, genetic engineering. We may have to genetically engineer our own genomes to survive those long times in interstellar space. Maybe we will find a future.